Hi everyone, I'm Lynette Schaefer, and in this video, I will take you through the LED as a light source. This includes how technology is different from traditional types of lighting technologies, and also look at the performance of LEDs and how they also are either the same or different than traditional light sources. So as you may recall, traditional light sources include incandescent, halogen, linear, and compact fluorescence, metal halide, high pressure sodium, and mercury vapor. What's very interesting is that every single one of these light sources can now be replaced with a very feasible option that is an LED solution, and that can either be an LED lamp or an LED fixture. So an LED replacement lamp looks very much like a traditional lamp in the fact that they have similar shapes with traditional bases, but they can also be integrated into lots of LED fixtures. So the days of replacing lamps are a little bit in the past, not totally, but they're going away. Not that you still can't purchase a replacement LED lamp or say maybe a tube-ready product that takes an LED lamp, but nowadays people, especially when it comes to new construction, are moving towards LED fixtures that have the LED integrated within them. So as you can see by this example here in the lower right-hand corner, this is a close-up view of a linear high bay with the lens peeled back so you can see the LED chips. There's no tombstones that are used. There's just a strip that has these LED diodes or chips on it, and that strip is typically either glued using some sort of adhesive or just screwed to the fixture. What's even more interesting about LED technology is that the technology behind LED is very different than any other traditional light source. So unlike traditional light sources, LEDs are not a lamp. They are actually a material called a semiconductor. If you're familiar with conductors, basically conductors easily allow electricity to flow through them, such as copper. And then there are insulators, which are the exact opposite. So electricity does not easily run through insulators, say rubber, for instance. Now, semiconductors are in the middle and they allow electricity to flow through them, but they need a little push because there's a little gap in the middle, as you can see here. So a general overview of how an LED produces light is that there are two sides. One that has a bunch of electrons and the other hot side is lacking the electrons, wants to get to the other side. But there's that gap in the middle, so the electrons have to get from one side to another. And when you apply electricity, that is when the electrons jump from the side and you have actual light. Very much different than traditional lights now, or traditional light sources. Now, the advantages of an LED far outweigh the disadvantages. There are, of course, the fact that LEDs are very efficient. They are available in a lot of CCTs and even colors like Christmas light colors, right? They provide instant on, they last for a very long time. There's also no UV with LED light sources. They can dim fairly easily. You've got to be a little bit careful, but they're not terrible. They're definitely a lot easier than HID light sources. Now, they are available in lots of shapes and sizes, and bases and wattages, and LEDs are also a directional light source, which we'll talk about that in just a minute. Now, the only real disadvantage of an LED is that they are affected by ambient temperature. As a matter of fact, LEDs are not fans of hot temperature. All LEDs also require a driver, similar to how fluorescents require a ballast. So going back to LEDs being a directional light source, why is this so important? Well, it's because traditional light sources are an omnidirectional light source where you have light coming out in all directions. And this is true whether it's an incandescent, if it's a fluorescent, if it's an HID, you have light coming all the way out of that lamp source or light source. Going back to LEDs being a directional light source, you don't have the same sort of situation going on. So when you put a traditional light source in a fixture, you can see you can lose a lot of light because a lot of that light is being either lost up or on the sides of the fixture and not getting down onto the work surface. As a matter of fact, you can have up to 40% lumen loss. Now, we'll get back into LEDs being a directional light source in just a second. So let's first of all deep dive a little further into LEDs as a whole. So this is what an LED chip or a diode looks like. Depending upon the size of the fixture or the lamp, there can be just a few of these little diodes, or there may be a whole bunch of these little guys. Each LED little chip here produces light and usually has some kind of protective cover. You can kind of see that. That's a very close-up image, the little one on the left-hand side. This little protective cover is actually called the primary optic, and the primary optic basically serves to protect and also shape the output of that small little LED diode or the LED chip. As you can imagine, these chips or diodes, they blast a ton of light, and they do need that cover, but they actually almost need additional optics in order to really push the light in the direction that you need it to go in. We're going to talk about that in just a little bit. But anyway, these chips are also responsible for producing the color of the light, meaning the CCT, or otherwise the blue, the red, the green, like you have maybe with Christmas lights or something. As a matter of fact, LEDs can produce about any color imaginable, which is pretty crazy, but it can. That includes your typical 27, 3000, 4000, 5000 Kelvin temperature, CCTs. Now, manufacturers use different colors of LEDs and different materials of semiconductors to control the energy level to produce the light color and to produce the light. The color light that comes from these semiconductors really just depends on that specific semiconductor material that's used. It also kind of depends on the current that's being supplied to the LED chips. The point is, I guess, with all that being said, is that most manufacturers do not use, say, like a colored lens. They used to at one point, but not anymore. Most of it's all done right on the chip itself and through the semiconductors. But anyways, that's the biggest thing that I wanted you to take away from that. Now, LEDs are much more efficient, as I mentioned, as many of you probably already know, because not only, they use less energy, but they are also that directional light source, which means you can put that light exactly where you need it, making the lumens from an LED light source all usable light. As you can see with this particular picture, those are all LEDs, and those LEDs are all shining directly out from the lamp. If that was a HID, traditional HID lamp source, you would have light going out in all directions, and that's a lot of wasted light. So the key thing to take away here is that usable lumens from a traditional light source do not equal usable lumens from an LED light source. So let's just take an example. Let's say you have a 3-lamp T8 and it produces a total of 8,550 lumens. So you have a 3-lamp T8 fixture. Each of those together, I should say, each lamp together produces 8,550 lumens. And that's what it says on day one, okay? Problem is that the 8,550 lumens, one, is never making it down to the ground because so many of those are getting lost inside the fixture due to lumen, depreciation, or just lumen, issues with getting it through the lens or whatever the case may be, right? There's a lot of things that go into play. So when you're looking at replacing those 3-lamp T8s with a new linear LED T8, you don't need a combination of 8,550 lumens. As a matter of fact, because the LEDs are a directional light source, you could probably get by with about, 5,000-ish lumens instead of 8,500 lumens. So just kind of keep that in mind when you're recommending an LED light source from a traditional light source. Not all usable lumens are the same when it comes to those technologies. So the question is how do you get all of those lumens on the work surface? Well, you use things like lenses and reflectors and diffusers and, of course, optics. So nearly all light sources have a lens, and the lens is usually like some sort of like transparent or translucent material, and is used to direct or diffuse light. Unfortunately, whether you're using traditional light sources or LED light sources, unfortunately, lenses can trap heat, which can be problematic, especially when it comes to LEDs. And of course, lenses can also get dirty and dusty, right? So the next thing that we have is a reflector. Now, the reflector provides a reflective surface to direct or spread the light from the lamp or the LED out onto the surface and into the space. Parabolic reflectors primarily focus the light toward a point, while other reflectors spread the light out. It just depends on which one you're using. Now, if you're familiar with, say, like a PAR lamp, PAR stands for parabolic aluminized reflector. Typically, you find those in a PAR halogen lamp. And it's basically just that shiny material in the inside of the lamp. Now, some LED fixtures also use this to help kind of push the light onto the surface. Now, when it comes to fixtures, traditional or LED, it doesn't matter. Reflectors can be used to basically push the light onto the work surface. That's why they're used. And also nowadays, most LED fixtures actually have a reflector integrated into the fixture instead of using these big reflectors that you see here, right here on the screen. So that's a kind of an old school way of helping push the light down in more of a high bay type application. The good news is that a lot of these are no longer being used, so you don't have to worry about doing that. Now, if you are using a halogen, you can also add a lens to that, or I'm sorry, if you're using a reflector, you can also add a lens. All right, so let's move on to a diffuser. Now, this is any material that scatters the light, okay? It can be different types of materials that do that. The main purpose of a diffuser is to diffuse or spread out the light. It makes basically bright and really harsh light a little softer. And it also helps kind of make it illuminate a wider area as well. It also sometimes helps with unwanted glare. It's very uncommon to use a lens and it's not uncommon to use a lens and a diffuser together. As a matter of fact, in a lot of our LED products, you'll see that they actually have a diffuser and a lens. The diffuser is there to help with the glare. The lens is there to kind of help, get some of that light also out and disperse it a little bit further. And then the last one we have are optics. Now, unfortunately, the light from LED's primary optics that we talked about before, that's just like a simple cover. And the LED itself is usually way too broad. The light coming out from that is way too broad for most applications. And it's not directed onto the work surface the way it should be. So although it's a directional light source, you can imagine that little LED chip is just basically just scattering all the light out of it, but it's not being directed to a useful space. So what happens is that what people will do, what manufacturers do, is they'll use a secondary an optic, which consists of sometimes just a lens. Sometimes it will consist of like a reflector. All of these things can help the light and really also does help the light get onto the work surface. It also magnifies the intensity to be more concentrated. So it does actually get to the work surface and you achieve the light levels that you want to do. But all four of these things, whether it's a lens, a reflector, a diffuser, optics, all of these things kind of work together. The other thing to kind of keep in mind is that more and more LED fixtures are having something that's called or include something that's called TIR. And TIR optics stands for total internal reflection. This is basically a flat, small lens that consists of a reflector, and it also has a lens that helps push the light in certain directions. This really does eliminate the need for these bulky reflectors that you see here on the screen. And it's a much more cleaner kind of look too. And that you see a lot in newer LED fixtures. So again, the lens, the reflector, the diffuser all contribute to the lighting levels of the space and the light distribution of the space. All right, so now let's move into the components of an LED light source. So there are 5 main components of an LED light source. The first component of an LED light source, whether it's a lamp or a fixture, are the optics. Now, some LED products like this replacement area lamp only has a lens, but other LED products will incorporate other optics such as a reflector, a diffuser, the TIR optics I just talked about, which again stands for total internal reflector. And that again just means that the lens and the reflector are together in one unit. Other LED products may also include a diffuser, and then optics, of course, are also used to take the light, magnify the intensity, and it directs it to the targeted surface. Now, LED chips are another component, and we just talked about those chips and what they look like. And those, again, are responsible for producing the light, whether that's a certain CCT color or color. And it also determines, how much lumens, are going to be coming out too of the fixture. Now, of course, some or actually all LEDs have to have some kind of heat sink. And this is used with LEDs and it's designed to absorb and disperse excess heat away from the LED diode and into the heat sink. So too much heat will damage the LED and the phosphors. And basically when that happens, it results in a lower light output. It also reflects in changes in color temperature or color of the light coming out of the LED diode, or it can have a significant decrease in life expectancy too. So heat is not your friend. The heat sink is, in this particular example, is a combination of these fins that you see here, as well as this gray stuff, which is a potting compound and is used for heat control, and it's also there to protect the components as well. So next is the driver, and this is very similar to a ballast. Sometimes too, and it can actually almost look like a ballast. Sometimes they're just a little bit smaller than what a traditional ballast looks like, but they are a driver. And some LEDs may also just use a circuit board too. This lamp here in this example happens to just be a circuit board. Now the driver's main purpose is to control the circuit. It also supports dimming and other control functions. Many also have built-in surge and thermal protection, which protects the fixture from, say, lightning strikes or extreme heat conditions. Some fixtures actually have additional thermal protection, and that's always a nice little added feature. Now, as a matter of fact, the other thing that's interesting about drivers is that they are intelligent enough that if the fixture is getting too hot, it will actually reduce the light output so that the system continues to maintain this longevity, and it will do what it needs to do to cool down if it does get to be too hot. Now, you're also going to learn that some replacement LED lamps will work on existing fluorescent ballasts. So although I am saying that all LEDs have to have a driver, there are some replacement lamps that will work on existing fluorescent ballasts. So just keep that in mind, and we'll talk about that again a little bit later. So lastly, we've got the housing, and the housing basically houses everything, but it also can act as a heat sink, and it also protects the LED lamp or the LED fixture from the outside elements as well. And here's just another example of all of these components using this fixture instead. You can see here that we've got the optics, the LED chips, the housing, and the heat sink. And in this case, the back of the fixture is where the driver is, and it happens to just be a circuit board that you can kind of take a look at as well. They're not always like this, but sometimes they are. All right, next up, we have another little example, and that is this actually happens to be a strip fixture. So the question is can you determine what each of these components are? So let's look at the first one here. So what is the top one? Well, that of course is your optics or your lens. After that, of course, we've got the LED chips. Then of course, we've got the driver. As I said, sometimes they do look very similar to a ballast. And then we also have the housing. And of course, in this particular case, the entire fixture is acting as a heat sink, and that of course is there to help disperse the heat as a whole. So speaking of life ratings and heat and longevity and all that stuff, let's talk a little bit about how traditional light sources compare to LEDs from a life rating standpoint. So first of all, LEDs do not fail or burn. I shouldn't say that. Let me back up. LEDs can fail. There's no doubt about it, but they don't burn out. All right. So if the system's running properly and everything's working properly, those LEDs will actually continue to burn for nearly forever. That's very much unlike other traditional light sources. Most other traditional light sources, the lights just burn out eventually, right? Additionally, with LEDs, they do lose lumen output, and that lumen output gradually decreases over time. Now, that process for that light to decrease is much, much longer than most traditional lamp sources. So let's talk a little bit about how you rate LED life, because it's not like traditional light sources where you have 50% of them, burn out. That's not at all how that works, actually. So the life of an LED is actually based on L70, L80, or L90. L70 is the IES approved method, which is calculated based on lumen depreciation. And of course, lumen depreciation refers to the loss of the original light output that occurs over time. So generally speaking, it's established that the human eye can only be sensitive to about 30% lumen loss, okay? Anything less than 30%, your eye can't detect that. Anything greater than 30%, your eye is gonna pick that up. So that is why L70 lifetime is approved by the IES. Now, lifetime ratings of an LED is dependent upon many variables, such as operating temperature, drive current, and the technology and materials used in the construction of the products. Of course, heat can have a major effect also on life of an LED. And that is why manufacturers do everything they can to help dissipate the heat. So now going back to this whole L70 rating. So L70 again is approved by the IES. It's not that you can't use L90 or L80, but L70 is the approved method. All of them are very similar, whether it's L70, L80, or L90. So let's see what L70 actually means. So when the LED is producing 30% less lumens than it did when it was brand new, this is what we refer to as an L70 life rating. So if L70 equals 50,000 hours, that means the LED is going to be producing 30% less light at 50,000 hours. If the rating was L90 equals 20,000 hours, that means the LED will be producing 10% less light at 20,000 hours. And if it was L80, it would be producing 20% less light at however many hours. That's how that works. So in summary, LEDs are, typically the light source of choice these days. Most traditional light sources can easily be replaced with LEDs, whether it's a replacement LED lamp or a brand new fixture with the LED integrated within. LEDs are much more efficient. They last longer. They provide the full spectrum of color, and they are much less expensive. And that is why they are so much more common than they used to be, years ago. Also, I don't believe I mentioned this, but most LEDs achieve about an 80 CRI. However, there are some energy codes that require the lamps or fixtures to achieve 90, such as California JA8, and you will learn about that in another training video. Thank you. And if you would like a course completion certificate, please email me, and also just be sure you notice that there's 2 N's in Lynette. Thanks, everybody.